Today's objectives are to learn how to find the arc length in the arc length formula and understanding how and why the arc length formula works. Here we have the graph of y is equal to f of x, and we're trying to find the length from A to B on this smooth curve, also known as the arc length. What we have learned from calculus and integrals is that a line or curve can be seen as the path of a point in motion. To find the length of a smooth curve between 2 points, we can integrate an infinite amount of these points in motion. Let's call these points in motion ds. From A to B, integrate all the points in motion. So, let me pick a point in motion. So, this is the point of motion we're going to call ds. Now, let us approximate that ds is a line. And of course, it's an approximation because we're actually dealing with a curve, but we're treating this a line. So this is similar to how in the Riemann sums, we approximate the area of a rectangle. So, using an approximation, I'm going to turn this into a triangle to mine some information out of here. And how I'm going to do that is I'm going to denote something for dx. No marker. Dx, so that's the change in x in context to ds. Dy, that's the change in y in context to ds. So what can we do with this? Using the Pythagorean theorem, which is this. And let me just tell you guys that this a and b is unrelated to this a and b. What is related to this a, b, and c is dx, dy, and ds. So I can plug these values in because the Pythagorean theorem is using a triangle. Specifically this kind of triangle. ds squared. Now, I have this statement here, which tells us something, but it's not very useful in finding the arc length. So I'm going to turn this into something like, I'm going to turn this into a formula that is useful in finding the arc length. So in order to do that, I need to find something that is equivalent to ds. So let me isolate ds. Now here, we have something that is very close to some familiar elements that we can manipulate and use. We have a dy, a dx, and another dy and another dx. So it's close to something that we know how to use, but not quite. So I'm going to manipulate this a little bit more so that we have something we could use as a formula. So what I'm going to do is I'm going to pull out this dx squared. Now, you might look at this and say, how are you going to pull out dx squared out of these two elements when there's only one dx squared here? There is inherently a dx squared within this dy squared. Let me show you how that works. Just make that clear. D and that's a y. All right, so here you can see when you redistribute the dx squared, that it cancels with a dx squared here. And obviously it takes the place of this one. So that's how there's inherently a dx squared within this dy. Now this is very convenient because, let me just set this equal to ds as you guys know. This is very convenient.
Action.
So what I could do is get rid of this square here because it's under the square root, and I'm going to pull out the dx. So what we're left with is 1 plus, let me make that clear, 1 plus dy over dx squared is equal to ds. Very convenient because we can plug it in to here. And now we have a full integral that we can integrate. Let me just rewrite that for y'all.
Action.
And I put the dx down. Alright. So, now we have our equation. You see how we got there. And this is no longer an approximation. We are now taking an infinite amount of ds's, not a set amount like the rectangles or like the set amount of ds, a set length. Now, whenever we're presented with an equation that is y is equal f of x, all we have to do is take the derivative, plug in the derivative right here, and we will get the arc length. Thank you.